Do you always understand why your IDE is sometimes making certain suggestions? Today, we'll look into a specific quick fix that the C# compiler suggests. CA1859 suggests that you should use concrete types instead of more abstract interfaces or base class types. I found that a lot of developers don't really understand this suggestion, what it means, why it could be an improvement, or not make any difference at all, and why sometimes it shows up and at other times it doesn't. So if you are also not perfectly comfortable in answering these questions, then join me for a few more minutes and I'll show you everything you need to know about this quick fix. More importantly though, you'll be able to apply this knowledge yourself in other places where the quick fix suggestion may not be coming up at all. Let's look at a small example. This is a typical case that comes up a lot in normal programs. We do something here in this case, since it's about performance, we're going to measure this later. And let's just create a list of 10,000 numbers, but it's a list. And we define the return type here to be IEnumerable. And lo and behold, this is our CA1859. Sorry, it's in German here, but it's the same error everywhere. So this is basically saying you return this interface here. But it would be much more performant if instead you use the concrete type, the list here, and say, oh, that's the one you want to have here, because that's much better and more performant. Now, you could also quick fix this and, and go in here and change the signature here. You could disable it, ignore it as usual with all these warnings. And you can try to understand it and find out what it means. Why does it impact the performance even? And why is it suggesting it here? And for example, now it's also gone. Sure, this doesn't need to be public, could be made static, but there is no more talk about this return type needing to be a list. If I do this and make it private, now it suddenly seems to be an issue. So how does public or private suddenly impact the performance? Is that a thing? So let's take a closer look. Let's see, we have some benchmarks here that we can look into, which are different usages of this numbers method and how it deals with this return type. So we can just call it and then basically ignore the result. That hopefully doesn't take very long in terms of performance. A usual case is somehow loop over it and do something in the loop. So obviously the performance depends heavily on what you do inside of the loop. So here we just compare it by not doing anything and just measure how long does it take to go through this loop. And then we can of course count how many numbers we have using the count operation. That's about it right now, which is already sufficient. So let's run these benchmarks and take a look at the results. Okay, so let's take a look at this first group of benchmark results we have here. As you see, there's one obvious result in the meantime of these. The looping over 10,000 numbers is of course the slowest one by far. But just calling it versus counting is so fast, but still the call is slower. On the other hand, you see the standard deviation on these measurements is like super high in comparison to the actual mean value. So it's more or less about the same. So just as we expected, looping over the numbers, really slow, everything else pretty fast. This will be pretty fast to change, so suggested change would just be turn this into a list. You see there's a little bit of an error coming up, but that's just my configuration that this one is already available on the list in a more efficient manner, but we won't do that for now. Just leave it like this and accept that it's basically the same code in the benchmarks after we change the return types. So let's run the benchmarks again. And just as the warning says, we get better performance. To loop over something when you have the list as the return type is about 3 to 4 times faster than the previous value we got. On the other hand, just calling it, doing the count, none of these seem to have made any significant difference at all. Like, it's pretty much exact same value, same standard deviation behavior, completely unchanged. Okay, so as we promised in the beginning, let's take a little bit of a deeper look into this. So why is loop over so much faster or slower depending on these types? First of all, let's take a look at the IL code that's been generated for this by the compiler. So you see that this is doing a call virtual here, reaching out. Right now we have the list, so the fast version, to the lists method to get an enumerator. After that, we basically have another loop here because we want to loop over these things. And what's crucial are these two call lines here. So these are calls to the enumerators getCurrent and moveNext method. And those are pretty fast, like your normal array indexing operations. But it's the call here. Now, if we change this to the enumerable and rebuild so we get the IL code updated, our numbers will still at the beginning get this enumerator, but you notice that it's now doing this through the enumerable, not through the list. And then there's pretty much the same code. It still loops over, it still calls out to, now it's called getCurrent and moveNext here, and it's on the enumerator interface, of course. But since this method is actually on an interface, that is where the performance difference comes from. Because you see here at the beginning, this is no longer a call, it's a call vert. So basically what this means is the interface itself in memory isn't a thing really. There is no place where the implementation resides. For an interface, you have to look at the concrete class that implements it. And there you will find the compilation of the code that does it. So to see this difference in action here, it's like, oh sorry, numbers. If you call getEnumerator, which this IL code basically does from the for each, then you end up in the interface, which is of course implemented by our list class that we return on the object of the list class. And if you compare that to using the list and then call getEnumerator, if I jump there, I end up right at the code. I end up right here. And the fun thing is that both variants, the enumerable as well as the list, they end up calling this piece of code to get the enumerator. It's just that now it knows that it's the enumerator, whereas on the enumerable, it only knows that there's an enumerator available. So again, interface versus concrete type. And just having this difference between a call vert, taking an extra lookup to find out like what object do you have at runtime? Oh, it's that class. All right, then this is where the code is. It's like this small indirection, but that is a lot slower. In large amounts of calls, it sums up. Okay, so let's get back to the beginning where we said this suggestion isn't always coming up. Like if it comes up, like here, you can certainly replace this with a concrete type and get a better performance out of it. So every call has a call vert indirection, versus the concrete type doesn't need that. It's a tiny little bit faster. If you do a lot of things with it, it'll be a lot faster, of course. So that makes perfect sense to replace. But then why does it go away if I declare this as public instead of private? Now it's no longer suggesting to make this because there's another trade-off involved now, and this is a typical interesting trade-off that we want to do in terms of programming. We want to have good designs. So as soon as you make this public, the information that you are having a list here in the implementation becomes a private hidden implementation detail of your class. You do not necessarily want to expose this to the outside world by making it publicly known that this thing is actually a list, the concrete type, Because as soon as you do this, you violate what we call the information hiding principle. You just tell everyone in the world how you implemented this in your class, which also means that everyone else using this numbers method on the outside can actually force you into having to keep this as a list, because they rely on these listings. So they do things like very simple like this, because, well, it's a list, I can use that property. If later on, and that could be months or years down the road, but eventually you decide that this data structure internally in your class may not be optimal, you want to do something better, well, you still have this concrete type list here that you have to satisfy. So you cannot change it later to something like this easily, because now you see a random place in the code somewhere else is no longer compiling, because it used to rely on this concrete type. And that's the whole point of having interfaces in object-oriented programming, after all. So you can do these replacement and substitutions basically without anyone needing to know about it. And that, of course, goes at the cost of a tiny little bit of performance, which we normally don't care, because this is so much more powerful in general in your projects to have these interfaces and be able to take any kind of implementation that you want and freely change it without anyone having to care. But the cool thing is that most major languages optimize the crap out of this anyways. So if we do a count on the IEnumerable, for example, and we actually do use a list, if you look into what C# does here, it's actually, instead of just starting to iterate right away, it's in fact actually checking the type of the object at runtime and says, like, maybe this doesn't need an expensive iteration through everything and counting menu. Maybe it's a collection, which the list is, of a certain type, and then I can actually use this property. So there's a small if here, and then it goes straight on to the count property of, for example, our list that we would have done with a concrete type. So yes, you have the indirection call, but no, you do not suffer the loop through everything cost here at all if you use a list. Right? So that still gives you the basic idea of doing all of these things. And why we have these hierarchies of, for example, these types is, as long as you still keep collection kind of as the basic type of what you return of your enumerable, this will still be really fast for counting. No matter what kind of implementation you use behind the scenes of your public method that is exposed to the outside. So that's why the warning goes away in those places, because you don't really want to optimize for performance at the cost of making your project really hard to change in the future. I hope you enjoyed this quick walkthrough through the CA1859 error or suggestion. Now you finally understand what it really means, what's going on behind the scenes, and why this sometimes appears or disappears, and I hope this will help you in your daily development. So thank you very much for watching, and have fun developing.